by looking at the tendencies around the mean. When you're in the lab taking measurements or taking 100 measurements and then, or looking at a paper that somebody else had a mooring and they looked at how variable things were. So on small scales, when you don't do it over all the ocean, things tend to be rather normal.
So I was wondering if that's the case, and you can just take the two extremes, and then that will reduce the amount of simulation.
That's correct, but then you'll have the worst case only. But you want something that's just not the worst case. You want to know, on average, how wrong I am. That's the worst case is not necessarily a good representation of that.
Yeah, it just feels the most honest one, the worst case scenario. Because then you're saying this is the worst and my model is
That's fine. But it's not. But if I had to guess a value, I would not give the same probability of being near these worst than I would near the center. But no, it's all good. And I mean, there's a thing to remember. You know, people put 95 confidence interval around data, which is wonderful. But remember that that means that in 1 out of 20 cases, you can be outside of them. And it's normal. It's totally okay if you're out. Doesn't mean the data is bad if you're out of a 95% confidence interval. 1 of 20, 1 out of you guys is going to be out there. You're 20. Okay? So it's okay to be outside, to have a point outside of the 95% confidence interval. It will happen on average 1 out of any 20 realization. It might be the first one you pick out that's going to be out there. Doesn't have to be the last one. Anyway, use statistically logically. If you don't know the underlying distribution, use non-parametric. Statistics does not prove any point, but it can give you a sense of likelihood of hypotheses and about relationship. I strongly encourage you to study hypothesis test and Bayesian methods. This is where a lot of the field is going, and they seem to be. And beware that hypothesis tests, the p-test, the student t-test, and all those are often misused. And there have been a lot of paper on it recently. I don't know if you've seen them. P-value misunderstood and misused, a dirty dozen 12 p-value misconceptions. The ASA, this is the American statistician statement on p-value, context, process, and purpose. Those of you who use p-value to establish strength in relationship. And this was in Nature last year. Statistician issue warning on p-values. So, because people use these statistics in ways that are not correct. They tend to establish causality, tend to assume that if your p is less than something, it means you proved a point. You made it true. You know what's happening, and you don't. There's always finite probability that your things are not the way you think they are. Anyways, but we did not get into hypothesis testing, but this comes into that. And many of you do use those p-tests, so just be aware. Yes?
When I studied ecology, we were taught to be afraid of non-parametrics because the power reduces, and they're always like, try to stay with a parametric test for hypothesis testing as much as you can. So you seem to be actually...
I'm advocating for non-parametric because it does not, if you don't know the underlying distribution, you're in safe territory.
But then you run into a risk of having more false positives when you have hypothesis tests with non-parametric.
Well, it turns out that a lot of people are running into false positive with normal, using parametric statistics. I mean, this is part of why all this came out, is that people were using it completely wrong in terms of inferring what was happening. So I try to not use any of this. I use the simplest statistic I can. Again, if I cannot make a point very simply, my point is at best weak. So if I don't see an obvious relationship, I'm very careful about saying anything. And again, with optical data, because all these instruments will give you data no matter what you do. If you don't see it in another instrument also, you have a very weak point, if at all. If you're with your float, if you see a structure in backscattering that you don't see in chlorophyll, I would not publish on it. Seriously, it's just very. There's all kind of things that can happen with those data that we didn't explore yet as a field. That unless you're Your confidence only increases when you see it consistently in other measurements, oxygen, that are related. They don't measure the same thing, but they're related. You expect certain things that happen. And this is why on the package we have so much redundancy. I mean, we have backscattering and total scattering. They should move the same as we have more material in the water. If one goes south and the other goes north, it's very likely that one of them is not doing what it's supposed to, if not both. And you don't know which one. Yes?
Do you generally run a statistical test to determine if, say, your data is parametric or not, like fitting a normal distribution, just quickly to just see if you want to even just go with the default of saying it's not non-parametric?
I very often look at the histogram of distributions, yes, of anything I measure. I do a probability diagram, and then immediately you see if it makes sense or not.
I mean, do you just look at the histogram though, or I mean,
yes,
a really simple test?
there are tests. There are tests, and you can do the test for normality. You can do the test for many things, absolutely. And it depends on when you do a transect here in the river, you're going to get very different population as you go through. And depending on where you sampled more, that data is going to be more. So if you look at global distribution of data in CDAS, for example, a validation data set, they're completely skewed for coastal. And you get bimodal distribution, even though those bimodalities are not what you expect in the global ocean. It's simply because they're skewed by the biases of sampling. We have more, in all these data sets, there's more summer data and more coastal data than anywhere else in the ocean. There's no ocean in the winter. There's no remote sensing in the winter. There is, we just don't have the data to. So always be aware of that. But yes, always plot the histograms. Always, 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 just to get a sense of how much things vary. And if it's important for you to do a normality test for the point you're trying to make, do a normality test. As you say, it's not hard. Use logic. The thing is, use your brains. Don't take a recipe and assume, oh, this is what Emmanuel does, I have to do it too. No. You have your data, your problem, your issues, and just learn. And this is why I love Impressital. There is no recipe. They call it in America, but there is none. Just tell you what works sometimes, why, what are the pitfalls, what to think about when you look at your data. And this is what I try to convey here, is that there is no one way. Just think about what makes sense to you, and be able to convince your reviewers that you did the right thing. And your reviewer might suggest, no, I think you should try that. Okay? Fair enough. I'll try that. There's no, there is no, I know it's hard to get it, but it's that I cannot give you a recipe. It's annoying that I'm not telling you what's the right thing to do. But I don't want to, because I want you to look at, with open mind on your data and maybe figure out that what I was doing is wrong, But again, if you use simple tests, simple things that make sense, if you see an obvious relationship, there is a relationship. If you don't see an obvious one and you're trying to find one test that will give it to you and reject all the other tests because they don't, then you're forcing your opinion on the data as opposed to accept that, yes, data is noisy. It's, let's say, whatever, half an hour, unless you have more questions. But this is also, I consider this more of a fireside talk than a lecture.
I also comment, I don't think any branch of mathematics where personal, I would say, human built-in prejudices cloud the results more than in statistics. It's the usual thing of, well, there's only one chance in a million it's going to happen to you in a day. Like, let's say, being killed in a car. So you say, oh, that's never going to happen. But then, 300 million people in the U.S., that 1 in a million things is going to happen 300 times a day. So it's the low probability doesn't make it unusual that it happens. And then there's the people that buy lottery tickets because they say, well, somebody's going to win the lottery. I'll buy a ticket, and it'll be me. No, it's like one chance of, 10 to the 40th or something that you're going to be the one. So most people really don't think in statistical ways, and it's just human nature. So you see whatever it is, and you think, oh, that'll never happen, or it's going to happen, or data is a normal distribution or whatever it is. You really just have to look at the numbers and go with that.
For me, the classic thing is the fear from terrorism as opposed to driving. I mean, we die orders of magnitude more on the roads, and we don't beep about it. But somebody dies from a plane, and suddenly, we have a whole new administration that costs us $1 billion a year. Instead of investing in the number of people that die, which for me would mean invest in driverless cars, so we cannot run into each other. That's where I would like to see the investment, and it will save more lives than any TSA and all these things that we invented in order to stop terrorism. It's a drop in the bucket, terrorism, but in our psyche, we just cannot. This is acceptable. People dying on the road is somewhat something we accept, but we don't accept people dying from bombs. It's and risk analysis is a branch of statistics. It's totally a branch of statistics. But it's just our emotion comes into it. And our emotion come into data, and this is also part. We believe the data is proving, my theory, and we're gonna, if this test failed, it's because the test is wrong. It's not because my data, and we're gonna find it in our data. It's really, and this is why I trust papers where somebody took data they did not collect. More, and you talked about it the other day, than data people have collected, because people have a relationship to data they collected. They know it's right, it's better than anybody else's. So it's much stronger when it's not your data that you're finding a trend in. Anyways, my two preaching moments, coffee time.